Proxima Centauri is the closest star to us and is 4.2 light years away, or 40 trillion km. To reach it with the fastest next generation space shuttle, it would take 115,000 years. This gives us the dimension of the fact that cosmic travel, at least in the next few centuries, will not be realistically possible. However, we will be able to send microscopic space probes the size of a mobile phone or less. In fact, the main problem is in the relationship between the mass of the probe, speed, and energy needed. As the mass increases, to have an adequate speed, a quarter or a half of the speed of light, an enormous amount of energy is needed. Any sentient species in the universe would have the same problem. Considering that the first galaxies are supposed to appear after a few hundreds millions years after the Big Bang, and that our galaxy, nearly 14 billion years later, is at least a seventh generation galaxy, this same problem has possibly been faced by countless civilizations before on other planets. Civilizations thrived on galaxies from previous generations. That is, they will evolve through the levels of the Kardashev scale, progressively gaining control of greater amounts of energy. At the threshold of the passage between level 1 and 2 of the Kardashev scale, even the first far beyond our possibilities, they would still not be able to face even the journey from Earth to the nearest star. So, would they give up? Possibly not. Even for exploratory purposes, they could have accumulated all the energy available to increase the speed to a maximum, but would have reduced the mass to a minimum. And how much is the minimum possible? And this minimum is achievable. Absolutely yes. In fact, a probe of this type is already available to us. Indeed, it has always been. This is any energetically charged particle, such as a photon with infinitely small mass. Photons are elementary particles that make up light and other forms of electromagnetic radiation. They have no mass at rest, which means they have no mass when they are not moving. According to the theory of relativity, massless particles must travel at the speed of light. However, a photon can carry a minimal amount of information, its frequency and phase. And how can it bring us any useful information? We see this all the time through light. In fact, we can detect, see illuminated objects and understand many of their characteristics. How much information we can gather with a beam of photons depends on many factors, which as far as we know today are subordinate to physics, ranging from geometric optics to quantum mechanics. Thus, the extremes of space conquest range from a spacecraft of substantial size, capable of traveling at ridiculous speeds of the order of 100,000 kilometers per hour, to the speed of a photon, i.e., the speed of light 300,000 kilometers per second. But what could have been expected to be achieved by the use of active photon irradiation? This question opens up many deep and very interesting considerations and hypotheses. In fact, as we said, until the last century we used photons mainly in a passive way. We have recently learned to harness radio waves. As we said before, photons are elementary particles that make up electromagnetic radiation and physically carry it to send information. However, by sending structured information on a cosmic scale, or at least interstellar, it is not yet possible to hope to be able to detect its effect of feedback observing it from Earth. Probably our alien precursors will have encountered the same type of difficulty. Like us, they will have developed technologies not necessarily similar to ours, having to face in general terms the same problems, especially in terms of the energy needed for space exploration. During their technological evolution, they would also start by sending infinitesimal masses to achieve the maximum speed with the energy at their disposal. So maybe still photons? They would have used photons to receive information from the cosmos, as we do with our telescopes and antennas, then learned how to transmit information in the cosmos, the equivalent of our radio transmitters and lasers. Knowing that they could not receive intelligible feedback, what would they transmit? A trace of what they could have transmitted and how can be found in the studies of Del Judas on the water domains and the experiments of Montagnier, Vitiello, and Colantuono on electromagnetic DNA transmission. Both have shown that it is possible to transfer the information necessary to build life through electromagnetic irradiation. The appropriately irradiated water domains act exactly like a computer, but in a much more flexible and autonomous way. In fact, it is not necessary to send the genetic structure to observe its creation, as if the water domains already had the necessary information inside and the electromagnetic waves acted only as triggers. Clearly, there's a lot we don't know. So the hypothesis is that our alien precursors wanting to reach other planets sent the information to propagate life in the cosmos, so as to prepare the substrate on which to then transfer more structured layers. In other words, wanting to travel in the cosmos at the speed of light. Not being able to send anything massive, life could be built on another planet through successive irradiation. Then pilot its evolution until these life forms become suitable to accommodate the successive layers as the superior human abilities, the consciousness, and who knows whatever more, possibly memories and character of a specific group of individuals. Obviously, the act that they may have irradiated a particular planet does not guarantee that the process will take root there. On the other hand, the fact that we are here in itself excludes that this is impossible. That is, they would first build the hardware at the intended location and then send the software. So if we look for traces of aliens that have somehow reached our planet, we can say that until today we have searched in the wrong place. We must search not around us, but inside us, because we are the hardware.